So here I've just added a little simple script. This is our basic fuzzer script, and it's in Python. Basically what it's doing is it's pointing to the Python interpreter. It's going to import the socket library, and then it's just a little for loop that's going to send, it's going to first create a socket, and then it's going to send, it's going to connect to this guy right here, which is our test machine, the Windows machine, and Brainpan is running on 9999, and he's going to send a bunch of A's, in a for loop until it crashes. And we have our counter right here, and so this line will say, it'll keep track of how many bytes of A's have been sent until it crashes. So let's do this. Control X. I've already added the executable to it, and so now all I have to do is run it. So let's see what happens. Okay, and it says, looks like about 1,000 A's it crashed. So let's go double check that. Okay, and sure enough, we did crash it. Here's our A's. So we've proven that yes, it can be crashed, but we want to know exactly where it crashed. So we have to do a little more reconnaissance, and we have a couple of tools that we could use to help us find the exact spot of where it crashed. So I'll show you that really quick. Right now, I'll just close this up and we'll just get this guy ready to go again. We continue our fuzzing. So I'll load up Brainpan. I like to load it this way just because sometimes this thing acts a little funny. Okay, so now it's running, so it's ready for us to attack it. So I'll just go back to Kali. And now we will modify our fuzzer. So we want to know now, we saw that it looked like it crashed somewhere around 1,000 A's or something like that. Actually, the first time it was like 900 A's. So what we could do, we need to find out exactly where in memory it crashes at. So we're going to use a tool. It's actually a Metasploit module that will create a unique pattern for us. So we'll just send a unique pattern of characters to this buffer, and then when it crashes, we will be able to see exactly where it crashed at. So hang on. So we're going to use a tool. It's a Metasploit module called pattern create, and then that'll let us create a unique pattern of just different characters, and we'll be able to see exactly where it crashed at. So I'll show you the path to get there. Alright, so I put that in there, and that you see that length argument, so I put in 1,000, so it's generating a unique pattern of 1,000 characters right now. So it already did it. So what I'm going to do with this is I'll copy this into a little text file. I'll put it over here. Alright, so it's there hanging out. And then I'll just add this back to my script. So we'll comment out this line. I like to do that so that just kind of, you know, I can keep it kind of neat. So if I want to, you know, use it again, I can just use it again. And I'll just go down to the next line and create a new payload variable. Alright, so now instead of sending our A's, now we're going to send all this junk. So let's see what happens. Okay, so it looks like there's a crash. Let's see what the deal is here. Alright, there's our unique pattern. And this is the memory address where it crashed at. So let's make a note of that. It's 357-24134. That's going to actually be what's called our offset. So now we'll go back and use the same tool, essentially. Let me just make a quick note of that. Alright, so I got this test box started again. I'll kill this one right here, and now I'll go back and show you some other cool stuff. So we just used the pattern create tool, so now we're going to use its buddy called pattern offset. And basically, let me clear this out for you. Basically, what the pattern offset will do is show us where that offset is in the memory for Brainpan, that number that we just copied down. So just to find it, you know, you can do it really easy. Just say locate pattern offset, and it'll find it for you. And then just kind of do the same thing just did a second ago. It's going to say, hey, you don't have an argument in there, and I know, well, okay, didn't do it that time. So this one is query, and I'm asking it, you know, where is 357-24134, 24134, and it should tell me where it's at in memory. Okay, so my offset is 524, so that's the memory location exactly where this crashed at. But we have to prove that that's our offset, so I'll show you how we do that. So we go back into our script, and again I will comment this payload out. I do that because I can just go back and, you know, use it again. So oops. So this time we're going to create a new payload. So the payload is going to equal A times 524, right? And then plus, let's see if we can overwrite it with 4 B's. So B, made it quick, sorry, made a quick error there. Got quotations around that. plus b times 4. We go times 4 because this will equal a byte. So we send 4 b's and that'll equal a byte. So plus b times 4, and then we'll just say times c for the rest. Alright, so this is our new payload, so we're going to send it A times 524. That should be exactly where it crashed. And then if we indeed have control of the if that is the correct offset, then right after that crash, the EIP should be pointing to here. We should see 4 B's. So let's see what we know what we're doing. Close this out, Control H. We had already set this guy up to roll, so let's just see what happens. Alright, abracadabra. Oops. And what part don't you like? Yeah, it doesn't like that C. So, hang on, let me do a couple things to my script. Rookie mistake. All right. All right. So we should see 4 B's if our offset is correct. So let's see what happens. Let's run our exploit again. I'm sorry, not our exploit, our fuzzer. Yeah. Okay. So a couple more rookie mistakes here that I shall fix, so hang on. Alright, so this is important. So originally we said it was about 1,000 or 900 that crashed it. So let's say 900, I have to do a little bit of math here, minus our offset, and then minus the 4 bytes that we're sending with our B's, our 4 B's, which is 1 byte actually. And then we could say times C. Okay, let's see if that fixes our script. All right. All right, sure did. So now we should be able to go over to our test machine and we should see 4 B's. And sure enough, so our offset is correct because as you see right here, we have 4 B's. So we had all of our A's executing these different registers. So here's our A's. The ESP register is a really important register. And then here's our instruction. So what does that mean? Well, that means that we have proven that we have control over the pointer, which is this guy right here, the EIP. So if we're going to write an exploit or be able to get the machine to execute the code that we want, say perhaps a reverse shell, then this is the next instruction right here. So this will tell it to point to whatever we have, say where the C's are right now. So conceptually, the C's are going to be what contain our shellcode, but we haven't gotten there yet. I'm just kind of giving you a heads up.